Early and foundational computer programming is strictly linear. Code reads from top to bottom, executing every single line blindly, regardless of changing conditions outside the script. Real-world applications require branching logic. To be useful, a program must adapt to user inputs, shifting data, and unpredictable environments. The architectural solution to this limitation is the selection structure. It allows a deterministic machine to pause its execution, evaluate its current state, and choose a specific path based on that evaluation. This diagram shows how we model these structures. At the center is the decision statement diamond. A single input arrives, the system tests a specific condition, and the code splinters into multiple potential execution paths based on whether that condition is true or false. Relational operators and logical combinations allow the computer to evaluate its state against hundreds of unique variables. This control flow provides the architecture for real-time responsiveness, allowing the software to react to changing data inputs. The most basic decision node is the single alternative selection, commonly known as an if-then statement. This flowchart shows how a bypass loop operates. The program checks a condition, like asking if it is dark outside. If yes, it executes the action block to turn on the lights. If no, it bypasses the block entirely and continues down the main path. These side-by-side examples show this implemented in Java, Python, and C++. The logic is identical across all three. If the variable temperature is greater than 80, the system prints an alert. If it's 80 or below, the program does nothing and moves on. When you need to guarantee one of two outcomes, you use a dual alternative, or if-then-else structure. This flowchart shows the path splitting in two. The machine must execute one of two mutually exclusive code blocks before the paths merge back together. In this voting age check, the compiler ensures only one block executes. The machine evaluates the state and picks one path. Notice the syntax differences. Python relies on indentation, while C++ and Java require structural braces to define where an execution block begins and ends. While programming languages vary wildly in their human-readable syntax, the underlying mathematical logic of decision-making remains absolutely identical at the machine level. To navigate these branching paths, the decision diamond has to compute whether a given state is true or false. It uses relational comparison operators. The green boxes show symbols for exactly equal or not equal. Crucially, a single equal sign assigns a value to a variable, but a double equal sign mathematically checks for equality. Mixing these up frequently breaks program logic. For numeric thresholds, developers use greater than and less than symbols. The left panel shows the critical distinction between checking if a value is strictly greater than a number versus greater than or equal to it. Relational operators act as the sensory inputs for the program. They translate continuous, real-world data, like a fluctuating temperature reading, into a discrete binary Boolean value that the logic gate can process. Evaluating a single variable works for simple tasks, but real-world systems often need to evaluate multiple overlapping constraints simultaneously. This graphic illustrates logical operators. The green AND block enforces absolute consensus. Every condition must be true. The blue OR block requires only a single true condition. Finally, the purple NOT operator inverts a truth value, efficiently verifying an absent state. These operators follow strict mathematical rules. The truth table in the top right demonstrates this rigidity. An AND chain yields a false result the moment any single input is false. There is no ambiguity. Logical operators provide the syntax to map nuanced human decision-making directly into efficient machine code. Combining relational and logical operators allows developers to flatten their code. Instead of nesting multiple if statements inside each other, a single line can define an inclusive range, like confirming a speed is between 30 and 60. But what happens to a computer's processing speed when it encounters a massive chain of AND conditions checking 50 different variables at once? The compiler relies on short-circuit evaluation, processing logic strictly from left to right. As shown in example 2, if the first condition of an AND chain is false, the entire statement is mathematically impossible. The hardware immediately stops and skips processing the remaining variables. Expert programmers leverage this behavior. By placing the condition most likely to be false at the beginning of the chain, they actively optimize execution speed. When a single equation mixes and, or, and not operators, how does the compiler avoid chaos? It adheres to strict operator precedence. There is a universally programmed order of operations. The machine resolves parentheses first, applies any not negations, and finally evaluates the remaining and or operators. These selection structures form the bedrock of software complexity. They act as the logic gates for everything from a simple thermostat to the routing algorithms of artificial intelligence models. Every single microsecond, thousands of new inputs stream in, system state is evaluated, and exact execution paths are dynamically chosen. Applying Boolean gates and short-circuit optimizations enables the development of autonomous systems capable of resolving complex, multivariable logic at high speeds.